So you will have heard this idea before, and it's really the amount of stuff we've got in a particular volume. It could be liquid, it could be a gas, but essentially it's a measure of how much stuff we've got in a particular space. So you might have heard of concentration when you talk about concentrated orange juice, or a concentration of gases has increased in a particular city because of the pollution. So the idea is that we try and measure how much stuff we've got in a volume. In chemistry, the units that we're going to use, well, we use grams per decimeter cubed. Decimeter cubes we'll talk about in a second, but a decimeter cube is the same volume technically as a litre, but we use it when we talk about solutions. You could also use grams per centimeter cubed. The one we're going to use the most, because we like the mole, is moles per decimeter cubed. Now you know that the slash means per, so that's number of moles in 1 decimeter cubed, moles per decimeter cubed. Mathematically, you can write that a different way. You can write mol dm to the minus 3, and it means exactly the same thing. It means moles per decimeter cubed. Okay? So we're going to try and find out, when we talk about solutions, how many moles of a particular substance, a solute, we've got in solution. Okay? Here's your moles concentration triangle. So we're going to use this triangle. This is the way that we're going to calculate the concentration of different solutions. So the concentration of a solution is the number of moles that we have divided by the volume. Or if we want the number of moles, we times the concentration by the volume. Or if we want the volume, we do the moles divided by the concentration. Okay, that's how the triangle works, isn't it? Remember the units. Concentration must be in moles per decimeter cubed, and volume in that case must be in decimeter cubed. There's the equation written in a slightly different way. It's the same equation. And just a reminder that 1 decimeter cubed is 1,000 centimeter cubed. 1 decimeter cubed, which is a litre, is 1,000 centimeter cubed, 1,000 milliliters. Get that stuck in your head. Okay, let's do some calculations. It's the best way to get used to these new equations, isn't it? So, calculate the number of moles of potassium hydroxide that must be dissolved to make the following solutions. We want 500 centimeter cubed of 2 moles per decimeter cubed solution. So what are these two things? 500 centimeter cubed is a volume there, and 2 mole per decimeter cubed is a concentration. So the thing that we're looking for is the number of moles. Okay? Remember, 1 decimeter cubed is 1,000 centimeter cubed. So we know that we have to convert centimeter cubed to decimeter cubed. So 500 centimeter cubed is 0.5 decimeter cubed. Okay? Moles is concentration times volume, as we saw, is 2 times 0.5, 1 mole. So we would have to add 1 mole of potassium hydroxide to 500 centimeter cubed to make a 2 mole per decimeter cubed solution. We could, at this point in a question, we could say, right, what mass of potassium hydroxide do we need? And we could use the moles equation to work that out, couldn't we? We're not going to here, but we could. Okay, another practice calculation. Calculate the concentration of the following solution of hydrochloric acid. So you've got 0.1 moles of HCl dissolved in to make 500 centimeter cubed of solution. Great. So what have we got? We've got a number of moles, and we've got a volume, haven't we? If we've got moles and a volume, we can work out the concentration. There's the concentration. Now you might want to stop the video for a second so you can work it out. So number of moles is 0.1. The volume of solution is 0.5 because it's 500 centimeter cubed. So we've got 0.2 moles per decimeter cubed. That's the concentration of the solution. A little note here just to remind you that mole per decimeter cubed can be written as big M. So whenever you see big M in relation to these concentrations, it means moles per decimeter cubed. That's the symbol that we use, moles per decimeter cubed. Okay, it's an abbreviation. Right, we have these two triangles that we can use in this question. We've got the concentration triangle and we've got the moles triangle. Okay. So it says calculate the concentration of the following solution. 5.85 grams of sodium chloride is dissolved to make 400 centimeter cubed of solution. Great. So the first thing we do is we find out the MR of sodium chloride, don't we? Which is 58.5. 23 is sodium and 35.5 is chlorine. Okay, great. So 1 mole of sodium chloride has got a mass of 58.5 grams. How many moles of sodium chloride have I got? Well, I can use the mole equation for that, can't I? Number of moles is the mass, 5.85 grams, divided by the mass of 1 mole, 58.5, which is conveniently 0.1 moles. Great. Now, I know I've got 0.1 moles, and I know what volume of solution I've got. So I've got a moles, and I've got a volume. Got to be careful here. 400 centimeter cubed, obviously, is 0.4 decimeter cubed. So we've converted the volume to decimeter cubed. So we use the concentration equation, moles divided by volume, 0.25, big M. Remember, big M means moles per decimeter cubed. Okay, check through that, make sure you can do it. Titrations are an application of these calculations, the concentration calculations. And a titration is a tool in chemistry, in the chemistry armory for, it would be a weapon in the chemistry armory, wouldn't it? It would be a tool in the toolbox and a weapon in the chemistry armory for working out the concentration of a solution we don't know the concentration of. So the concentration of a solution of unknown concentration. And the way that we do that is we use another solution of known concentration, which we can make up accurately. So we use one solution to find the concentration of another. And here's some of the equipment that you would use. A pipette for measuring out a fixed exact amount of solution, and a burette for adding an exact amount of solution. Okay, so we use an indicator to show us the end point of the reaction, and that's what we're going to use to, or the numbers, we'll use them to calculate the concentration. So the steps we follow. When you've got a titration, when you've got a calculation involving titration, then the first thing you need to do is write a balanced equation. Then you calculate the number of moles of the substance used of known concentration. So if we've got a concentration and a volume, we can calculate the number of moles we've got. We can use this number to find the number of moles of the substance of unknown concentration, and then we can find the unknown concentration. Okay, now that might not make too much sense to you until you see it in practice, so we'll do that now. Let me just talk to you a second about this. What we do in titration is you add 25 centimeter cubed, typically. In this case, it says of sulfuric acid, you add that to a conical flask. And then you've got sodium hydroxide in the burette, and you would add that slowly until the indicator changes color. So you know exactly how much sodium hydroxide you've added, you know exactly how much acid you had. Okay, so let's have an example. 25 centimeter cubed of 0.1 molar hydrochloric acid. So we've got a volume, and we've got a number, and we've got a concentration. So from a volume and a concentration, we can always work out a number of moles. were neutralized by 18.5 centimeter cubed of potassium hydroxide solution of unknown concentration. Calculate the unknown concentration. Okay, that's nice and simple. First thing we do, remember, first step was we write the equation for the reaction, don't we? There's the equation for the reaction. You can copy that down. Okay. So 1 mole of potassium hydroxide reacts with 1 mole of hydrochloric acid to produce 1 mole of potassium chloride solution and 1 mole of water. It's a 1 to 1 to 1 to 1 mole ratio. Great. Step 2. Let's work out how many moles of hydrochloric acid we had. So number of moles of hydrochloric acid, concentration times volume, 0.1 times 0.025. Now we're becoming experts now at changing these volumes. So 0.025 decimeter cubed is 25 centimeter cubed, isn't it? That gives us a figure of 0.0025 moles of HCl. Great. If there's 0.0025 moles of HCl, then there must be 0.0025 moles of KOH in that solution because it's a 1 to 1 mole ratio. So we've got 0.0025 moles of potassium hydroxide in 18.5. If we've got a number of moles and we've got a volume, we can work out a concentration. Moles divided by volume. There are the numbers. 0.0185 is 18.5 centimeter cubed divided by 1,000, isn't it? There's the final concentration. Okay. Now that makes sense because this is when I go back and check it. My concentration of my acid was 0.1 molar. This says that the KOH has got a slightly higher concentration, 0.135 molar. But we had to add less of the potassium hydroxide than of the hydrochloric acid. We had to add 18.5 centimeter cubed instead of 25. So it makes sense that the potassium hydroxide is slightly more concentrated so that the two of them balance out. Okay? Take your time, look back through that to make sure you understand the process. Read the pages indicated and answer the questions.